The next time you feel pain, remember this: another animal might feel nothing at all. Not because its body is magically stronger, but because evolution edited the alarm before it reached the mind. We treat pain as if it were a basic law of the universe. Touch fire, and it hurts. Step into freezing wind, and the cold feels hostile. So when we imagine another creature being burned, frozen, bitten, or crushed, we lend it our own suffering. We picture a tiny human trapped inside a different body, feeling a smaller version of our pain. But nature does not work that way. Pain is not a physical substance floating in the world, waiting to enter every nervous system. It is a biological message, built by the body and interpreted by the brain. And across the animal kingdom, evolution rewrites that message again and again. Sometimes it turns pain down until a deadly warning becomes meaningless background noise. Sometimes it turns pain up until a tiny wound makes the whole world feel dangerous. And sometimes it changes pain so completely that poison becomes protection. To understand this, we have to start in one of the strangest places on Earth. Deep underground, in crowded tunnels with almost no fresh air, lives the naked mole rat. It is hairless, wrinkled, nearly blind, and packed into colonies that can feel more like insect nests than mammal homes. The air in these tunnels can build up with carbon dioxide at levels that would torture a human face. In our eyes, nose, and throat, that gas can form an acidic sting that feels like burning, but the naked mole rat lives inside that chemical discomfort as if nothing is wrong. Its skin and nerves are famously insensitive to acids that would make most mammals recoil. It can also ignore capsaicin, the chemical that gives chili peppers their burning heat. For us, capsaicin is a red-hot lie told by a plant. It tricks the nervous system into shouting fire, even when there is no fire. For the naked mole rat, that alarm has been partly disconnected. In a tunnel where acidic air is normal, constant burning pain would not be helpful. It would be like living beside a smoke alarm that screams every hour of your life. So evolution did something brutally practical. It made the alarm quieter. The naked mole rat does not survive by being heroic. It survives because its nervous system refuses to panic at the place it was born to live. But the desert has an even stranger example of pain being rewritten. The grasshopper mouse is small enough to look like prey, but it hunts like a monster. At night, it stalks bark scorpions across the sand. The scorpion strikes with venom that would cause intense pain in many animals. The mouse gets stung, shakes, attacks again, and eats the creature that should have stopped it. The secret is not that the venom fails to enter its body. The secret is that the mouse's nerves process the venom differently. In this animal, the scorpion's chemical weapon can end up blocking the very pain signal it was meant to create. The attack becomes part of the mouse's defense. A poison designed to hurt becomes a kind of accidental painkiller. This is the first crack in our assumption. Damage and pain are not the same thing. A body can be struck, cut, burned, or stung before the mind decides what that damage means. Scientists often separate this into two ideas: nociception and pain. Nociception is the body detecting potential damage through nerves and reflexes. Pain is the conscious, unpleasant experience that may arrive after the warning is processed. When your hand touches a hot stove, it pulls away before you fully understand what happened. That instant reflex is not a philosophical experience of suffering. It is a protective circuit doing its job before thought catches up. The suffering arrives later, when the brain turns the signal into something personal. This distinction matters because animals can react to damage without necessarily feeling pain the way we do. And that question has haunted science for centuries. In the 17th century, René Descartes argued that animals were like biological machines. In that view, a crying dog or struggling fish was not truly suffering. It was only producing motions, sounds, and reflexes. That idea is comforting because it makes human cruelty feel smaller, but the more carefully scientists study animals, the harder that comfort becomes to defend. Fish were once a favorite example for people who wanted pain without feeling. A hooked fish thrashed, but skeptics said it was only reflex. A fish lacked a human-like neocortex, so they argued it could not truly suffer. Then researchers began asking a better question: not whether a fish has a human brain, but whether it behaves as if pain changes its priorities. When trout are exposed to irritating substances around the lips, their behavior can change dramatically. They breathe faster, stop feeding, rub their mouths, and act as though the injury matters. When pain relief is given, those behaviors can reduce. That alone is interesting, but the stronger evidence comes from choice. Some fish normally prefer complex, sheltered spaces where predators would have a harder time finding them. Empty, exposed water is dangerous. But when injured fish are offered relief in the risky place, some will abandon safety to seek it. They trade protection for comfort. That is not a simple twitch. That is an animal weighing one danger against another. Goldfish shocked in a feeding area can avoid that place for days. They return only when hunger becomes stronger than fear. Their world is not a simple machine of stimulus and response. It is a world of memory, pressure, hunger, danger, and relief. This does not mean fish pain is identical to human pain. It means the old certainty that fish feel nothing has become very difficult to defend, but the story becomes more unsettling when we move to animals with stranger bodies. A hermit crab lives inside a stolen shell, and that shell is not just shelter, it is armor, home, and survival equipment. If a crab receives a mild electric shock inside a low-value shell, it may abandon it quickly. But if the shell is valuable, the crab may endure more before leaving. If it smells a predator nearby, it may endure even more. That tiny animal is caught between two terrible options: stay with the shock, or leave the shell and become exposed. Its behavior suggests more than a blind reflex. It suggests a nervous system comparing costs. Even after escape, some crabs attend to the shocked area of the body. The more we study them, the less simple they become. Then we reach insects, where certainty becomes dangerous in both directions. Insects can seem almost impossible to relate to. A caterpillar may continue eating while parasites consume it from within. A male praying mantis may continue mating after losing its head. Cockroaches can survive injuries that would be psychologically unbearable to a mammal. Their behavior makes them look like machines built from reflexes. And in some ways, that may be close to the truth. Insect brains are astonishingly efficient, but they are also tiny compared with ours. A human brain has roughly 86 billion neurons. A fruit fly has around 100,000. With that kind of nervous system, evolution has to be economical. It cannot build every creature with the same emotional machinery as a human being. An insect may detect damage, escape danger, and protect a limb without experiencing suffering as we know it. But here's where the honest answer becomes less satisfying. Scientists still debate how much and what kind of pain insects may feel. The safe conclusion is not that insects are empty machines. The safe conclusion is that their inner world is probably not a miniature version of ours. Their bodies remind us that pain is not one universal language. It is a set of biological dialects, and some of the strangest dialects belong to the animals of the deep ocean. Cephalopods forced scientists to take animal experience more seriously. Octopuses, squid, and cuttlefish are not simple bags of reflexes. They solve problems, explore objects, remember places, and control bodies that seem almost impossible to manage. The octopus is especially disturbing because it appears so intensely aware of itself. If an octopus injures an arm, it can focus attention on the damaged place. It may groom the wound, protect the limb, and retreat into a den while healing. When local anesthetic is applied to an injured area, that attention can change. The octopus seems to know not only that something is wrong, but where it is wrong. Its pain is localized, useful, and connected to precise action. The squid lives under a different rule. A long-finned squid is not a den-dwelling surgeon of its own body. It is an open-water animal surrounded by predators, built for speed and escape. If a squid gets a small injury, it cannot calmly retreat and tend the wound. A predator may already be closing in, so its nervous system can spread sensitivity far beyond the damaged area. A tiny injury can make the entire body react as if danger is everywhere. Touch the squid far from the wound, and it may still explode into escape. To us, that sounds like a nightmare. To the squid, it may be the difference between life and death. Its suffering, if we can call it that, is not designed for comfort. It is designed to keep the animal paranoid enough to survive. At this point, pain stops looking like a single experience. It becomes a control panel. Turn it down in a toxic burrow. Rewire it against a scorpion. Spread it through a squid body when predators are everywhere. The question is no longer, does damage hurt? The question is, what kind of warning did evolution need this animal to hear? And once you understand that, temperature begins to look just as strange. We think heat and cold are simple facts. Fire is hot, ice is cold, and winter hurts. But the feeling of temperature is not the temperature itself. It is your nervous system's interpretation of molecular motion. A thermometer measures heat. A body decides what heat means. This is why an Antarctic bird is not just a suffering human in feathers. An emperor penguin standing in a blizzard is not necessarily experiencing cold the way you would. Its body, feathers, blood flow, and nerves belong to a different climate reality. The same wind that feels cruel to you may be ordinary weather to the animal built for it. Temperature enters the nervous system through tiny molecular sensors on nerve endings. These sensors act like gates. At certain temperatures, they open and allow electrical signals to begin. Humans have cold, sensitive channels that help make mild drops in temperature feel uncomfortable. Other animals can carry related sensors with very different settings. A temperature that makes a human shiver may feel neutral to a frog. The world has not changed. The alarm threshold has. The 13-lined ground squirrel takes this idea to an extreme. To survive winter, it hibernates underground while its body slows almost to a stop. Its heart rate can plunge from hundreds of beats per minute to only a few. Its body temperature can fall close to freezing without waking it into panic. For a human, that would be a medical emergency. Our cold alarms would scream because staying awake and generating heat might save us. For the squirrel, Waking too often could waste the energy it needs to survive the winter, so its cold sensing system is tuned for silence. Place this animal on a cold surface, and it may show little interest in moving away. Not because cold has disappeared from physics, because cold has lost its emotional command. The same animal also has unusual heat tolerance in its pain system. In many mammals, painful heat alarms begin around temperatures that can threaten tissue, but some species shift those alarms higher. Ground squirrels and certain desert animals show heat-sensing systems tuned differently from ours. A surface that would feel brutally hot to a rat or human may not send the same urgent message. This does not mean the animal is invincible. It means its nervous system has different rules for when discomfort becomes worth action. Extremophile animals are not spending their lives in heroic agony. They are not constantly enduring the apocalypse. Their bodies have made the apocalypse feel normal. Saharan silver ants run across desert surfaces so hot that most insects would quickly die. Iceworms live inside glacial ice and can be harmed by warmth that would feel gentle to us. Each creature is calibrated to a narrow version of the world. Comfort is not universal. It is local biology. And for some animals, temperature is not merely comfort or discomfort. It is geography. A fruit fly zigzagging through a room can look random and stupid to human eyes. But the fly may be navigating invisible temperature structures in the air. Its tiny antennae can detect extremely small changes in warmth. Because the antennae are so small, they rapidly match the temperature of the surrounding air. A slight difference between left and right can tell the fly which way the thermal world bends. A pocket of warm air can become a wall. The fly turns as if it has struck something solid. To us, the room is empty. To the fly, it contains invisible architecture. But the most dramatic temperature specialists do not avoid heat. They chase it. In the early 20th century, a massive oil fire in California burned for days. As flames lit the night, people noticed small black beetles flying toward the inferno. These were fire chaser beetles, insects drawn to freshly burned wood. They mate near fires and lay eggs in charred trees. For their larvae, burned wood can be a nursery with fewer living enemies. Most animals flee a forest fire. These beetles treat it like a signal. The obvious question is how a tiny insect finds fire from such great distances. Smoke can drift unpredictably. Flames may not be visible through daylight, trees, or distance. So some fire-seeking beetles use infrared radiation, the invisible heat glowing from burning wood. Hidden near their legs are tiny heat-sensitive organs. Inside them are microscopic structures that respond when infrared energy warms them. That warming can create mechanical pressure on sensitive nerves. A distant fire becomes a message inside the beetle's body. Even the motion of flight may help prime the system, pushing the sensor closer to firing. To the beetle, a forest fire is not just destruction. It is a beacon, a mating ground, and a nursery all at once. This is where temperature becomes more than a feeling. It becomes information. And for warm-blooded animals like us, that information can be dangerous. Millions of years ago, mammals and birds evolved bodies that produced their own heat. Warm blood gave us endurance, activity at night, and freedom from some environmental limits. But it also turned us into glowing targets. To blood-feeding animals, your body is not hidden in the dark. It is leaking warmth. Parasites do not need to understand you as a person. They only need to follow the heat. Some microscopic worms can move toward temperatures that resemble the warmth of a living host. To them, a foot on warm soil can be a doorway into a body. The vampire bat is a far more cinematic version of the same idea. It stalks sleeping mammals in darkness, moving on all fours like a tiny hunter. Before it bites, it must find a place where blood runs close beneath the skin. Its nose carries specialized heat-sensitive structures that help detect warm spots on a victim. Evolution modified a heat sensor that, in other mammals, helps warn of painful heat. In the bat, the threshold is shifted toward the warmth of living tissue. A blood vessel becomes a hidden line of heat beneath the skin. The bat does not need to see the artery. It can feel the invisible warmth of the meal. Ticks use a quieter, more disturbing strategy. They climb grass or leaves and wave their front legs like tiny antennae. For a long time, people thought they were mainly following smell. Smell matters, but research suggests heat can also guide them. Some ticks have tiny sensory pits on their front legs that can help detect infrared radiation. In effect, your body heat may become part of the trail they follow. Repellents such as DEE may interfere with more than smell alone. They can disrupt the tick's ability to use heat cues. You are not just hiding your scent. You may be scrambling part of its thermal search system, but the most famous heat hunters are snakes with facial pits. A pit viper does not merely feel warmth as comfort or danger. It uses heat to locate prey in darkness. On either side of its face are deep pits with delicate membranes suspended inside. Those membranes are loaded with sensitive nerve endings. Warm objects cast a crude infrared pattern onto them. A mouse in the dark becomes a moving patch of warmth. The snake's brain combines this heat information with vision. It does not see a clean science fiction thermal camera image. It sees a rough, blurry, useful map of warm bodies against cooler backgrounds. That blur is enough. A blinded rattlesnake can still strike toward a warm target with terrifying accuracy. The snake's strategy makes the system even stronger. It can wait where cool shade meets warm ground, making prey stand out more clearly. Some vipers use cold backgrounds, even the open sky, to make warm birds easier to detect. In a strange twist, thermal sensing can work especially well when the snake's own body is cooler. The animal may be physically sluggish, yet its prey can glow more clearly in the thermal world. It becomes dangerous in the very darkness where we feel safest. By now, the pattern is impossible to ignore. Pain is not simply damage. Cold is not simply temperature. Heat is not simply warmth. Every nervous system edits the world according to what the animal needs to survive. Even the dog sleeping near you may live with hidden thermal abilities. A dog's nose is often wet and cool, and that cold surface may help it detect faint warmth. In controlled tests, dogs have shown they can distinguish warm objects from cooler ones at a distance. Your dog may not only smell the room, it may sense invisible traces of heat inside it. That friendly animal beside you is not sharing your exact world. It is living in a version shaped by nose, nerves, memory, and instinct. This is the real lesson hidden inside pain and temperature. We do not experience reality directly. We experience the version our bodies can afford to build. A naked mole rat can live where acid would burn our faces. A grasshopper mouse can turn a scorpion's weapon against itself. A squid can make its whole body hypersensitive because hesitation means death. A hibernating squirrel can ignore cold that would wake us in terror. A beetle can treat a forest fire as a glowing invitation. A tick can search for the heat leaking from your skin. A snake can strike at warmth in darkness. None of these animals is breaking the rules of reality. They are revealing that our rules were never universal. We call fire painful because our nerves translate it that way. We call ice cruel because our bodies are tuned to fear it. We call injury suffering because our brains turn damage into a personal alarm. But another creature may hear a whisper where we hear a scream. Another may hear a scream from a wound too small for us to notice. Another may not care about cold, but may see your warm blood shining through the dark. The world is not one shared movie playing equally in every mind. It is more like billions of private simulations running at the same time. Each body filters the universe through its own sensors. Each brain decides what matters, what hurts, what attracts, and what must be ignored. So the next time you feel pain, heat, or cold, do not mistake that feeling for reality itself. It is only your version of reality. Somewhere nearby, another creature is walking through the same world and experiencing a completely different universe.